your surface is defined as a graph. Z is g of xy for some function g, which it was in this case. Then you can work out more easily what RU cross RV is. It's always going to be minus partial g with respect to x, minus partial g with respect to y, and then 1. So you can go for details of the cross product. For this case, computing your RU and RV, which have this relatively simple form, it always turns out to be this. So the z component is 1. So computing RU cross RV just gives you always upward orientation. So if a problem asks for downward, you just negate this. So, and generally I'm only going to specify upward or downward orientation for a surface like this, where it's easy to determine what's upward, what's downward. Now, so we could have just done this, where z in this example was square root of x squared plus y squared. However, where are x and y defined? On the circle of radius 1, the unit circle. So if you went ahead and did it this way, and you tried to compute the integral over your parameter space of x, y, z to the fourth, dot product with RU cross RV, and then negate it because the problem asks for downward orientation, dx dy, or not dx dy, really it's dA. Right. Well, d is a unit circle. So you would still have to convert to polar coordinates to evaluate this double integral. So like I said earlier, you can switch to polar coordinates at the beginning or switch to polar coordinates later on, because your parameters x and y, your parameters are x and y in this case, they're defined on a circle, not a rectangle. Whereas u and v, from how we did it this way, those were defined on a rectangle. So we had nice simple limits. There was no need to do any conversion of the integral to polar coordinates because we were already in polar coordinates to begin with. All right, so any surfaces that we will deal with has an orientation. So this, what I've drawn here is an example of an orientable surface. That at any point on the surface you have a well-defined unit normal vector n that varies continuously over a surface. So this is one side, and if you negate all the normal vectors, then you have unit normal vectors pointing out of the other side. So, yes?
I just had a quick thought, okay? Slightly off topic. Oriental culture, is this where this came from? Orientable?
Versus orientable?
Yes.
I have no idea, and I doubt it.
Okay.
All right.
Oriental.
Now, informally, an orientable surface is two-sided. There's two visually easily identifiable sides to it. Unlike the example I did last time, the Mobius strip, which is a surface that only has one side. So what that means is, even if you're varying a unit normal vector continuously along the Mobius strip, what happens is at any point on the strip, you actually have two normal vectors that you can get. But here, we have to commit to one side or the other. So we say, we're going to use this normal vector, we can look at any point on the surface, continuously varying a point, continuously varying the normal vector, and we get all of these normal vectors on top, or we choose the other side, and we get these normal vectors that are pointing down. So we're not going to be concerned with pathological counterexamples like the Mobius strip. we're going to care about two-sided surfaces like this, where if you change your orientation from one set of normal vectors to the other, that changes the sign of any surface integral. It's just like with curves. Curves had an orientation too. So if you had a line integral of a vector field along a curve going from point A to point B, if you change orientation to go from point B to point A, that changes the sign of a line integral of a vector field along that curve. So it's the same idea. All right. Now, there's one other kind of surface that we're going to be dealing with a lot that I need to say something about, and then we'll do an example involving it. At least we can start it. A closed surface, just like we talked about closed curves a while ago. So if you have a closed surface, I'll do an example, I'll draw an example here. So now we have a cone where the base is included. Right. So for a closed surface, it doesn't really make sense to talk about upward and downward orientations because it's closed, because you have something going on all sides. Instead, what we talk about is outward and inward orientation. So here we have an outward unit normal vector. So this would be the outward unit normal here. For a base, it would be pointing down. Whereas you could switch orientations and point inward. So these are inward unit normal vectors. I guess if I'm going to call everything a unit normal vector, I should shorten these. Just so they're the same magnitude, roughly. So those are the two choices of orientation with a with a closed surface, pointing in or pointing out. So for example, let's take a look at the unit sphere. Okay. Now, if I choose a parameterization of a sphere, I go ahead and compute RU cross RV, either it's going to give me the unit, the outward unit normal vector or the inward, one or the other. It all depends on what parameterization you choose. And different choices could lead to different outcomes, outward or inward. So let's choose a standard parameterization for a sphere. Well, we'll stick with the unit sphere. So x is cosine theta sine phi, y is sine theta sine phi, and z is going to be cosine phi. So this just comes straight from spherical coordinates. Now I won't go through all the details now, but if you go ahead and compute r theta cross r phi, then, and you evaluate it at the point 1, 0, 0, that's on the sphere, the vector that you get is 1, 0, 0. In that direction, it's pointing out. So, in this case, this particular parameterization, computing this normal vector, happens to give you the outward unit normal. On the other hand, what if I did r phi cross r theta? What is changing the order due to the cross product?
Changes the direction.
Yeah, it changes the direction, changes the sign. So that would have given me minus 1, 0, 0. That gives me an inward unit normal vector. Okay. Now, this vector, if it's cross product, it's not always going to be a unit vector. In this case, it happens to be. But really what we care about is what direction is it pointing away.